Okay, so today we are going to be talking about Riemann sums. Riemann sums are a method of approximating the area under a curve, or the accumulation of change. So say we have a function here, f of x, just it could be any function. What we're going to do is we're going to have our bounds a and b. So we're going to say x equals a and x equals b, and then we're going to have y equals 0. And these are the bounds of our function, and this is what we're trying to find, the area in between. So we want to find the area from y equals 0 to y equals f of x between the x bounds a and b. And what we can do to approximate this is we can split this into multiple different subsections. So we can call this here x1, this here x2, and this here x3. And then we can also say that our last bound is x4 and that our first bound is x0. So we can also say that between each of these intervals we have a delta x, which is going to be equal to b minus a, which are our bounds, minus n, where n equals the number of rectangles made, or subdivisions. So I said here rectangles, you may be thinking, oh, well, what do you mean rectangles? So the way that Riemann sums work is you turn these subdivisions here into rectangles, and then you get the area under each of these, and then you sum them. And so the way that you can do that is you can say delta x, which is our change in x, which is also our gap between each line, or the width of our triangle, multiplied by f times xo. F of xo, which we know a is equal to xo, is also equal to the height of this triangle. And now we can do this for each of our subdivisions as shown here. And that is supposed to be a delta. And you may be thinking, oh, well, we did it for xo, x1, x2, x3. What about x4, or our last bound? And the reason why we're not using x4 is because we're doing what's called a left Riemann sum, which means that we are coming from the left and that we are taking the height on the left side of each triangle. And our last bound isn't on the left side of any triangle. Thank you.